So last class, what we did was the generation of alternating voltages. So what we did was, first of all, alternating current or alternating voltage generation. We talked about the generation. Then we talked about its dependency on the speed of rotation of the prime mover. Right? And we also talked about how to calculate the RMS value. Then we also talked about average value for 1 half cycle. Right? This is what we talked about in the last class. Right? So let me probably reiterate a little bit about this so that we will be able to work out a few problems based on the concepts we learned in the last class, and then we'll go ahead further. Okay. So what we said was something like this. If I'm going to have a magnet, last time I had shown the magnet up and down. Now I'm going to show the magnet as though the magnet is residing like this. So this is North Pole, this is South Pole. Okay. And normally in a machine, you are going to see that you cannot have the poles floating in air. Obviously, it cannot float in air. So it has to be supported by a complete structure like this. And you can imagine as though it is a cylindrical structure which is extending into the board. Okay. And this is North Pole and this is South Pole. And you're going to have the magnetic lines, field lines going like this. These are the magnetic flux lines or field lines. That is how it is going to be. Now, I'm going to have probably a coil just extending again into the board. I can imagine as though it is going like this, and then it is, it is coming out like this here. So this is the coil that I'm showing, and it can have its plane exactly parallel to the lines of force, or it can be perpendicular depending upon what is the kind of direction of rotation. So if I just look at one coil, I can have that coil's one end here, the other end here. Okay. And if I am looking at this particular position and I am rotating this in this direction, very clearly I'm going to have this rotating like this tangentially, and I'm going to have its rotational direction like this. These two are going to be having the two directions like this. Okay. So if this is the way it is, this is exactly perpendicular to the line. So if you are going to have this magnetic field lines and the velocity exactly perpendicular to each other, only at that point, if I try to look at B times V, which is the velocity, B times V, this will have the maximum value when they are perpendicular to each other. Right? So we basically said that this B times V, and V is after all equal to R times omega, where omega is actually d theta by dt, or the way how the theta is changing. That is going to decide exactly what is the kind of rate of change of velocity that you are going to, rate of change of, the position you are going to have. So if I say that there are n revolutions per second, if you are going to have n revolutions per second, so you are going to have 2 pi radians, right? 2 pi n radians per second is going to be the actual way in which this is going to traverse the angle. 2 pi radians multiplied by n, so much of radians will be traversed in 1 second. That's what we were talking about, right? So from this, we basically said, if we are looking at B, L, V sine theta, that's what we originally wrote. So BLV sine theta is going to be the EMF induced at any position theta occupied by the conductor. That's what we said. And then what we did was to multiply this by n, where n was the number of conductors. Right? So we said B, L, V, sine theta. Sine theta actually we removed if we wanted to look at only the peak value, but let me have the sine theta also on, no problem. This multiplied by n. Now for this V, we replaced it basically by R times omega, or you can say 2 pi n. We basically use this as 2 pi n is omega. So 2 pi n times R. So I should be able to replace this by n, B, L and 2 pi n times R. Right? Multiplied by sine theta. So in general, what we can say is that if I am looking at the rotational velocity to be n revolutions per second, the induced EMF is going to be proportional to the number of conductors as well as the number of revolutions per second. Both of them are going to determine what is the amount of induced EMF at any point in time. And when we talk about the peak value of induced EMF, that is going to essentially give me B N L 2 pi R multiplied by capital N. Sine theta I have to remove. I hope I have not left out anything. N B L 2 pi N R. That's fine. So if I assume that I'm going to have this magnet extending, sometimes we have something like a claw. The pole is going to extend like a claw. So if it is going to extend completely like this, then I'm going to look at the entire surface of this particular inner cylinder on whose periphery I have inserted more and more number of conductors. Obviously, your generator is not going to have only 2 conductors. It will have multiple number of conductors. All of them may be connected in series. It depends upon what kind of connection I want to have. So if I have all of them connected in series, I'm going to have, the complete flux density. If I try to look at B as the average flux density, I have to multiply that by the complete area around the cylinder so that the total amount of flux is coming into picture. If I say that the total amount of flux is some phi and the surface area of the cylinder is the surface area which is only the surrounding area, not the 2 ends, that is 2 pi RL. This is going to be my flux density. So in which case I should say this B multiplied by 2 pi RL, that is going to give me the total flux. So this is total flux multiplied by N multiplied by total number of turns. This is going to give me the induced EMF peak value. Okay. So in general, what we are trying to tell in this particular generation of EMF, whatever we discussed, is that the EMF is going to vary sinusoidally as the position of the conductor itself shifts from theta equal to 0 position to theta equal to 180 position to back to theta equal to 360 degree position. So you are going to have, if you look at the voltage as such generated, it is going to have a sinusoidal wave shape. It is going to have a sinusoidal wave shape where the peak is going to be proportional to, the peak value is going to be proportional to the flux. It is going to be proportional to the number of conductors and it is going to be proportional to the number of revolutions per second. All of them are going to play a vital role in deciding what is the peak value of EMF that is being generated in a single phase generator, single phase AC generator. Okay. Now we have seen exactly how the EMF is generated. So if I apply this to a resistance, so now I'm going to connect a resistance in the terminals of the generator. So I should look at it as though I have a generated EMF which is alternating. Alternating generated EMF will always be specified with the sign like this. Okay. And I'm going to connect it to a resistance. This is what I'm doing. So Ohm's law will be followed still. So if I'm going to have V equal to Vm sine theta, very clearly I'm going to have now I will be equal to Vm divided by R sine theta. So this is going to be actually Im sine theta. So if I try to draw the voltage and current across a resistance, I'm going to have essentially both of them are just the scalar multiplication of each other. There is hardly any difference in terms of where the zero occurs for the current sine wave and the voltage sine wave. They are going to be exactly in phase with each other. There is no phase shift between the voltage and current if I try to look at a resistance. They are going to be exactly in phase with each other. There is no difference whatsoever in terms of their waveform. Only thing is, one is a scalar multiplication of the other. This will be V divided by R. If I say this is V, this is going to be V divided by R. That is going to be my I. That's all. So there is no difference whatsoever between the two in terms of phase displacement. Whereas, if I try to apply the same voltage to an inductance, or if I try to apply the same voltage to a capacitor, how are they going to behave? This is what I need to look at next. Okay. So if I am going to have, let us say a current I equal to Im sine omega t. I have to first of all explain this, why we call this as omega t, first of all. So we said that the conductor, if you look at it, it is initially occupying a place where theta equal to 0. And as time goes by, it is going to occupy maybe theta equal to some other, theta 1. Then after some time, it is going to occupy theta equal to theta 2 and so on. It is going to occupy different places. Okay. And correspondingly, what we get is maybe initially sine 0, hardly any voltage is generated. Then it is going to become sine theta 1. Then it is going to become sine theta 2 and so on. This is how the voltage is changing. This is all a product of Vm. Vm multiplied by sine theta 1, Vm multiplied by sine theta 2 and so on. The rate at which you are going to see this particular conductor rotating, if I say that I'm going to have n revolutions per second as my speed of the prime mover, we said that 2 pi radians will be traversed within 1 revolution. Whenever I'm going to have 1 revolution, 2 pi radians will be traversed. So by then, if you look at it, my sine wave also would have gone from this 0, it would have passed through the peak, then it would have passed through the negative peak and it has reached again 0. This entire thing is known as one period of the sine wave. So this is going to be t. So I can say that for traversing 2 pi radians, it is taking t seconds. Okay. So I can say 2 pi by t will be the radians per second or velocity of, or the angular velocity of this particular prime mover. Or in one sense, I can also say this is going to be the oscillation rate of this sine wave, what we are generating using this AC generator. So the oscillation rate, whatever we are talking about, can be expressed as 2 pi by t, or I can say 2 pi f, where f is actually the frequency of the sine wave, right? And 2 pi f is going to be actually in terms of radians per second. So you can express the frequency in hertz, or the same thing can be equivalently expressed in terms of radians per second as 2 pi f. So if I say this is 2 pi f, the 2 pi f multiplied by t, because omega t is actually theta, d theta by dt is omega. I'm sure all of you know this. The rate of change of the angular position is going to be your actual angular velocity. So you can say that this sine theta can also be written as sine omega t or sine 2 pi ft. So the frequency can be inferred if I know what is the revolutions per second for my prime mover. So if I know the prime mover speed, I should be able to infer what is the frequency, what is the period of the sine wave, everything we should be able to infer. Okay. So if I say that in an inductive circuit, this is an inductive circuit and I am having a current which is corresponding to Im sine omega t. Okay. Now I know that the voltage across the inductance is L di by dt. This is how the inductance itself is defined. The inductance actually is defined as whatever is same as N d phi by dt. Rate of change of flux linkage and L multiplied by di by dt, they are one and the same. That is how the inductance is defined. So I should be able to write this as L multiplied by Im omega cos omega t. Right? This is what is L di by dt. Because I have this to be L di by dt, if I try to rewrite the whole thing this way, this is omega L multiplied by Im. I can write cos omega t as sine omega t plus pi by 2. I hope you understand, because I can show the cosine wave and the sine wave. They'll be one and the same. Only thing is, if this is my sine wave, right? My cosine wave will have maximum value right here. So I'm going to have the cosine wave somewhat like this. This is how the cosine wave will be, right? With the same peak value. So this is cos omega t Im. And this will be Im sine omega t. Both of them will exactly have the same peak, which is Im, but they will be shifted from each other by 90 degrees, cosine leading the sine by 90 degrees. Please remember, cosine leading the sine. So I should be able to write this as omega L multiplied by Im sine omega t plus 90 degrees or plus pi by 2 radians. Either way is fine. Right? So this very clearly tells me that this voltage omega L times Im, if I try to call that as Vm, right? Now we wrote basically in the case of resistance, Vm divided by R is Im. That's what we wrote in the case of resistance. So here if I have to write Vm divided by omega L equal to Im. So this omega L is specified as the inductive reactance in ohms. So this is the inductive reactance in ohms. Yeah.
How did you get that Im is equal to Vm, omega L, Im omega L is equal to Vm?
We are basically talking about VL, what is the voltage across the inductance. So if I am talking about the voltage across the inductance, and after all, inductance, capacitance as well as resistance, all of them are linear circuit elements. So if I give you a sinusoidal function or any other function, the voltage and current will be similar mathematical functions. They cannot be any different. So we are talking about this also as a sinusoidal function. So the peak, whatever of the voltage, we are calling that as Vm. That's all. The peak of the voltage if the voltage is also a sinusoidal function, this happens to be the peak of the voltage. So I'm calling that as Vm. Got it? Okay.
Yes, ma'am. So omega L becomes the reactance.
Yes, it will be the reactance in ohms. Only thing is, it is actually making a transformation with respect to the voltage. The voltage is actually leading by 90 degrees or pi by 2 radians as compared to current. So if I happen to draw what is the kind of voltage and current I am having in an inductance, if this is the voltage that I am having in an inductance, let me erase this. This is the voltage I'm going to have in an inductance. And if I try to draw what kind of current I'm going to have, the current is going to lag behind. So the current will lag behind like this. And the peak value, of course, if I try to look at this as Im, I'm going to have this peak value of Vm as omega L times Im, where L is the inductance value, omega is the frequency of the sinusoidal wave in radians per second, not in hertz. It will be in radians per second. Okay, got it? So this is the major difference between inductance and resistance. We are going to have a phase shift, the first factor, and the second factor is the resistance or the so-called impedance offered by the inductance is also a function of omega. Higher the frequency, higher will be the impedance offered by the inductance for the flow of current. So if I'm talking about a 50 Hertz circuit versus 500 Hertz circuit, for a 500 Hertz circuit, for the same value of inductance, the impedance or what kind of impediment the inductance is offering, it will offer a more amount of impediment. That's what I'm trying to say. That is because you are going to have a rate of change of flux also at a higher frequency. So it will generate more amount of voltage which is like opposing the current flow. Inductance always generates a voltage which is opposing the current flow. That is the reason why you are going to see that at higher frequencies, the inductance will be able to offer more amount of impediment to the current flow. Okay. Now let us try to look at the capacitance circuit. So if I again look at the capacitance circuit, if let us say I'm applying a voltage of Vm sine omega t. This is going to be the voltage that I am applying to the capacitance. We wrote that C times dV by dt, right? That is going to be the current. Fine. So we say that I times T is Q and Q is CV, from which we derive this entire thing, right? So if I say C I dt equal to C dV, we are writing C dV by dt equal to I, which is the current. Okay, so I should be able to write this as C Vm omega sine omega, no, cosine omega t, right? Cosine omega t equal to I. Right? So I should be able to say that Vm divided by 1 by omega c multiplied by sine of omega t minus 90 plus 90 equal to I. So I should be able to write this as Im, right, sine omega t plus pi by 2 or 90 degrees, doesn't matter. So I should be able to say that Im equal to Vm divided by 1 by omega c. So if I call inductive reactance as XL, which is equal to omega L, I should be able to call capacitive reactance as XC, which is 1 by omega c. So this is the capacitive reactance. And if I try to look at the voltage and current relationship, it is just the converse of what I get for inductance. This is inductance, voltage and current, where the current is lagging behind by 90 degrees, whereas here the current is going to lead by 90 degrees. Yeah.
How did you get E Vm omega cos omega t is equal to I?
See dV by dt. V is Vm sin omega t.
Okay, you differentiated that.
Differentiated, yes. Yeah,
Okay.
dV by dt. Okay. Yeah, so if we try to have, for example, a circuit which is having an AC source, and I have a resistance here, and I have an inductance here. Let us see. Okay. Please note that the current will be the same because it is the series circuit. It's going to be the same. Whereas if I try to look at what is the kind of voltage I'm getting across the resistance, the voltage drop across the resistance, it will be I times R. And what I get as the voltage drop across this, it will be I times omega L. But I cannot simply add IR and I omega L as a scalar addition. That is not correct. So if I have to actually look at it in terms of RMS value, I am going to have actually, let's say if I is a vector like this, for example, I will have the IR also actually in phase with this. Both of them are going to be in phase because we are not having any phase shift between the voltage through a resistance, voltage across a resistance and current through the resistance. Whereas if I try to look at what is the kind of phase shift I have between the voltage across an inductance and current through an inductance, I'm going to have voltage across an inductance leads the current by 90 degrees. That's what we said. Similarly, voltage across a capacitance lags the current by 90 degrees. So if I try to draw as a vector, I should draw it as though it is at 90 degrees leading position because we always take this direction, anti-clockwise direction as the positive direction normally. So if it is leading, I'm going to have this as I omega L. What is the magnitude depends upon what is the omega value and what is the L value. Both of them are going to decide how much is the magnitude of this. The same way, if I have to draw a capacitance voltage, I have to draw it as though this is I divided by omega C. So when we are doing the addition of voltages across resistance, inductance, and if I have a capacitance, we cannot simply do scalar addition. That's what I'm trying to get at. We have to do vectorial addition. So if I try to add, let us say IR to what is I omega L. So we have to use Pythagoras theorem. Basically, we have to essentially add these two as though IR whole square plus I omega L whole square root of that will be the total voltage. If I call this a source voltage, the source voltage will be here. This is how it will be. So we have to use necessarily the Pythagoras theorem whenever we deal with RL circuit or RC circuit, which are in series. Okay. Similarly, if we have parallel circuit for RC, we might have to use again Pythagoras theorem there. We'll look at that eventually. But before that, we'll try to take some problems from tutorial sheet, next tutorial sheet. The first problem statement is something like this. A coil of 100 turns wound along the periphery of a cylindrical armature of length 20 centimeter and diameter 2 centimeter is rotated at a speed of 1500 rpm in a uniform magnetic field having a flux density of 0.5 Tesla. So let me first of all write this. So number of turns is given to be 100. Let me again go back here. Number of turns is 100. Speed is 1500 rpm. Flux density is 0.05 Tesla. So flux density is 0.05 Tesla. Tesla is same as Weber per meter square. I hope you guys know that. So this is 0.05 Weber per meter square and speed is 1500 RPM, revolutions per minute. How much is the revolutions per second? Divide this by 60, 25. So this is going to be 25 RPS, revolutions per second. Okay. What else is given? It says cylindrical armature length of 20 centimeter and diameter of 2 centimeter. So dia is 2 centimeter. So radius is 1 centimeter. And we are going to have L. L is 200. What is given? 20 centimeter. So 20 centimeter. Okay. And what else is given? Let me check. Okay. So the axis of rotation being perpendicular to the direction of the magnetic flux. Calculate the maximum value of generated EMF. So maximum value of generated EMF. I think it is already there. We have derived this, if you may recall, 2 pi RL multiplied by B multiplied by blah blah whatever. So here number of turns is given to be 100. Please remember, always if it is a turn, the conductor goes like this, it turns around like that and then it comes to the other side. So 2 conductors make for 1 turn. 2 conductors make for 1 turn. So 100 turns means 200 conductors. You should remember that. Okay? Understand? So 1 turn always makes
tell again how to get the 200.
See, when you have a conductor, if I say that this is the cylinder around which the winding is made, one conductor sits here, it goes all the way, then it is going to be turned around. Okay? And then it is brought back to the other side. These two are 180 degrees apart. Okay? So if I say that the current is flowing in this direction here, the current will flow in the opposite direction here. So this entire thing makes up for 1 complete turn. That is why we said that if you look at the direction, basically, if this is rotating in this direction, here it will look as though it is rotating in the opposite direction. So here if dot current is induced, here cross current will be induced and vice versa. You will always have opposite polarity of each other as far as the induced EMF is concerned, because if you try to look at it here, it is going in upward direction of rotation, whereas here it is going in downward direction of rotation. So the two will always have opposite polarity of induced EMF. So that is the reason I told you that if I have by chance this as the polarity indicated for this side of the coil, if I may call this as side A of the coil, on the other side when I indicate, I will always indicate it as though it is like this. Okay, so these two are always connected in series addition. Please remember, this is minus, this is plus, this is minus, and this is plus. They are always coming in series addition. So the voltages will be added. If it is subtracted, you will have zero generation. No way you will have any generated voltage at all. So it will always come in series addition. That is the way it is going to be. So if there are 200 turns, that indicates that it is 200 conductors, because one conductor goes, it turns around and then it folds back into the conductor which is actually coming at 180 degrees opposite to the original one. That is the way it will be. Okay. This portion actually is a wastage because that is not going to have any magnetic field exposure, but it is a necessary evil. There is no other way. If I look at the magnet like this, one magnet is here, the other magnet is here, this is the North Pole, this is South Pole. This will extend into, the board like this. Now, if I look at the inner cylinder, which is consisting of the conductors. So this is going to have a conductor here. This is the return conductor. Please imagine this conductor is going like this. It will fold up outside the cylinder. The cylinder will probably extend until here, but outside the cylinder it will fold up and then it will come like this. So this portion of the copper which is folding up will never be exposed to any magnetic field whatsoever. It is outside of the cylinder. So there are two concentric cylinders. The inner cylinder is carrying the conductor, which is generally known as the armature. The outer cylinder is the magnet. The inner cylinder will be exposed to the magnetic field as long as the conductors are on the surface of the cylinder. The folding portion is going to be outside the cylinder. So obviously this portion is a wasteful copper, but it is a necessary evil. That's what I'm trying to say. Okay, got it? So when you calculate for the number of conductors, you have to use 200, not 100. So you should be able to definitely calculate what is the kind of EMF that is being generated from the expression we derived. I'm going to leave it to you. You guys calculate it. The next one, what is being asked is, what is the frequency and what is its period? How will you calculate the frequency? If I'm having 25 revolutions per second, there will be 25 oscillations in the sinusoid also. I hope you understand. For one revolution, there will be one cycle that will be traversed. So if I try to look at the sinusoid somewhat like this, right? So this will be traversed. This will be traversed actually 25 times. 25 times such wave will be traversed within 1 second. So I'm going to call this as 25 hertz. If there are 25 cycles per second, I can call this as 25 hertz. So the frequency is going to be 25 hertz and the time period is going to be 1 by 25. I cannot write this as 25 hertz. I should write this as 1 by 25 seconds. Is this clear? Any questions on this? What else is being asked? The magnitude of induced EMF when the coil is rotated through 45 degrees from the position of 0 induced EMF. So if you calculate what is the peak value of the induced EMF, that multiplied by sine of 45. That's it. Fine. Is that all right? So, yeah. Any questions? Okay. So the next question is, an alternating current waveform has a sinusoidal shape with the peak value being 14.14 ampere. Calculate its average value over 1 half cycle, RMS value, form factor and crest factor. So here the peak value is 14.14 ampere, right? So which means this is a sinusoidal current. I hope it is given as that. If it is not given, then it is a problem. I hope it is given as sinusoidal current. Yeah, sinusoidal shape, thankfully. So we calculated that IM divided by root 2 is going to be IRMS. Right? We calculated this by integrating like this, Im square sin square theta d theta integrated over 0 to pi, and we averaged it over pi and square root. So you can do it with either pi or 2 pi, either way it will work out to be the same, it's not a problem, and this will come out to be Im divided by root 2. So I can say in this particular case, IRMS is going to be 14.14 divided by root 2. Root 2 1.414, if you assume, you are going to get 10 ampere. That is the RMS current. Okay. Although the peak is 14.14, please remember, if I try to look at the heating effect of this current in a resistance, the heating effect will be equivalent to 10 ampere of DC, nothing more than that. So that's what we mean by RMS current. The heating effect equivalence we are trying to look at basically. Okay. If you try to look at the average value for positive half cycle, we calculated this as Im sin theta integral of 0 to pi, and we calculated over pi. This is what we calculated in the last class. So this will come out to be, I think, 2 Im by pi. That's what we got as the answer. So the same thing you'll have to do now. So I average, if I want to get, that will be 2 multiplied by 14.14 divided by pi. Okay. The answer what is given is 9 ampere. Please verify this. So please note that I average is always much less than IRMS. Only one waveform, it is exactly equal to each other, that is the rectangular or square waveform. If I'm going to have an alternating current waveform like this, if I try to calculate what is the average over positive half cycle and what is the RMS over the complete cycle, both of them will be one and the same. So normally you will find that I average will be less than IRMS except for square waveform. Okay. So the other things that are asked are form factor and peak factor. So form factor is generally RMS divided by the average value. So here it will be 10 by 9. And peak factor is whatever is the peak value divided by the RMS value. So that will be root 2. Because we already said that peak divided by root 2 is RMS. So peak factor will be peak factor or crest factor. Both of them are synonymous with each other. So peak factor or crest factor, both of them are going to be root 2 in the case of a sinusoidal waveform, and form factor will be 1.11 in the case of a sinusoidal waveform. Okay. The next question. I think this you should be able to do. Let us try to look at some inductance based calculation. A series combination of 20 ohm and 20 millihenry carries a current of I equal to 5 cos 500t plus 10 degrees. So let us try to write this. So this is 20 ohm and 20 millihenry and I cos 500t plus 10 degrees. That is what it is saying. Let me see. 500t plus 10 degrees. That is the current. 5 cos 500t plus 10 degrees. Calculate the total instantaneous voltage across R and L. First of all, let us try to look at this. So this is 5, not. So this is going to be the current. So what is asked is what is VR and what is VL. How will you calculate this? How will you calculate this? How will you calculate VR? Voltage across resistance. You get my point. You are having resistance. You have having an inductance. So you are applying a voltage, whatever. We don't know what is the voltage. You are being asked to calculate that. And the current is given. What is the current that is given? So the first portion that is being asked is what is VR. And the second portion that is being asked is what is VR. VR is I times R. That's it. Nothing more than that. So I should be able to write this as I times R. And R is 20. 20 times 5 is 100. So I'm going to have 100 cos 500t plus 10 degrees. There is no difference between these two. Right? Okay. How will you calculate VL? Yes.
Omega I.
Yeah?
Omega Li.
Omega Li. How will you get omega? What is omega in this particular case?
500.
500. Exactly. Because normally we write 2 pi ft, which is omega t. So here what is given is 500t. So I'm going to have omega equal to 500. Okay. And omega times L is how much? 500 multiplied by 20 multiplied by 10 power minus 3. Right? This is going to be my XL value. So how much is XL? 10? Is it 10? Yeah. So this is going to be 10 ohm. Okay. So I should be able to calculate this as, tell me how much it is. Omega Li. 5 multiplied by 10 is 50. Agreed. Cos of 500t plus
100.
Yeah. 90 plus 10, 100 degrees. Right. Now these two have to be added. Then you will be able to get what is the value of overall voltage. Okay. So this sinusoidal function, when I try to add or subtract, it is not going to be very, very easy. That is the reason why we are going to resort to something called complex representation. So we will be trying to indicate these vectors as complex numbers. So if I say that the resistance is something like this, the voltage drop across the resistance is something like this, inductance is going to have a voltage drop which is along the imaginary axis of the complex number because it is 90-degree leading. And if I am trying to look at what is the capacitance voltage, it will always have again along the imaginary axis but towards the negative side. So if I represent the voltages and currents rather as complex number, it will be much easier for me to add and subtract them. So we will slowly migrate to complex representation of sinusoidal quantities. So in the next class, we'll be looking at complex representation of sinusoidal quantities.